Driving fast is exciting. But the faster you drive, the longer it takes for your car to come to a stop. The screech of tires on the road lasts longer for a faster moving car. But why does it take longer for a faster car to come to a stop? 2 words: kinetic energy. The faster a car moves, the more kinetic energy it has. For a car of mass m and speed v, the kinetic energy, or the energy of motion, is Ke equals 1/2 mv squared. This is a quadratic equation. In order for the car to stop, work needs to be done equal to the amount of kinetic energy. Work is force times distance, and force is mass times acceleration. So the work needed to stop a moving car is mass times acceleration times the stopping distance. So mathematically, when a vehicle is brought to a complete stop, the following equation is generated. 1/2 mv squared equals m times a times d. Notice how the value of the mass divides out. Solve for d, the distance traveled as the car comes to a stop. This is the stopping distance. D equals v squared over 2a. But this equation assumes that you instantaneously step on the brakes. But there is usually a split second between the time you need to stop and the time you step on the brakes. During that time, the car is still moving at speed v. Assume that it takes 2/3 of a second to react. Our stopping distance equation becomes d equals v squared over 2a plus 2/3 v. Since car speed is usually expressed in miles per hour, we now need to adjust the equation so that the results are in feet, not miles. Multiply by 3600 over 5280, which converts from miles per hour to feet per second. Simplify to get the new equation. The values of a vary from 4 to 5. If you're bringing a car to a stop on a dry road, use the higher value. The stopping distance for a wet, rainy road uses the lower value. You'll see from the graphs that because stopping distance is based on the square of the speed, the faster you go, the farther the car skids to a stop. Accident investigators have to work backward. They know the braking distance by measuring the skid marks on the road. By measuring the skid marks and using the simplified formula d equals v squared over 2a, they can calculate the speed of the car at the time the brakes were applied. Then, taking these results and using the full formula, the total stopping distance is found. Alternatively, if an investigator knows the total stopping distance, they can find the speed of the car by solving the quadratic equation for v. Suppose that at an accident scene, the total stopping distance for a car is determined to be 250 feet. Was the car going over the speed limit of 65 miles an hour at the time of the accident? Let's use the TI-84 to solve. Turn on the TI-84. Before graphing the function, let's change the window settings. Press the Window button, set Xmin to 0, Xmax to 100, Xscale to 10, Ymin to 0, Ymax to 400, and Yscale to 50. We want to solve the quadratic equation 250 equals 0.2324 v squared over a plus 0.4545 v. For a dry road, the value of a is 5, and the quadratic equation becomes 250 equals 0.04648 v squared plus 0.4545 v. For a wet road, the value of A is 4, and the quadratic equation becomes 250 equals 0.0581 v squared plus 0.4545 v. So let's graph these two functions to represent the two possible road types. y1 equals 0.04648 v squared plus 0.4545 v, and y2 equals 0.0581 v squared plus 0.4545 v. Press the y equal key and input the two functions shown. Make sure that no other functions are active. After you have input the functions, press the graph key. Your screen should look like this. To solve the quadratic equations graphically, we want to find where these parabolas intersect y equals 250, which is the stopping distance. So press on the y equal key again and input 250 for y3. Press graph. Find the intersection points for each parabola and the horizontal line. In each case, press the second key and the trace button. Select the intersect option. Use the navigation arrows to identify the two functions, pressing enter for each graph. Press enter one more time to see the coordinates of the intersection point. From the coordinates of the intersections, we see that on a dry road, the speed of the car is more than 68 miles per hour. But for the wet road, the speed of the car is about 62 miles per hour. The accident investigator would need to know the condition of the road at the time of the accident to determine if the car was going faster than 65 miles per hour.